Good afternoon. This video is going to cover SPSS walkthroughs of three kinds of analyses. The one-way ANOVA omnibus test, the chi-square test of goodness of fit, and the chi-square test of independence. These data will be the same as those used in other videos that are on my playlist about walking through statistical calculations of those three tests. So we're going to start with the one-way ANOVA, and I'm going to show you the descriptives on the group membership and also on the problem scores so that you can see their relationship to what we've already looked at in the other video. So the scenario here is that students were assigned in equal numbers to one of three groups for instruction. In one, they were in a cold room. In the second, the first was, I believe, 50 degrees. The second was a moderately temperature room of 70 degrees Fahrenheit, and the third was in a hot room. So we can see that under descriptive statistics, if we look at the frequencies of group membership, and we had 15 total cases, 5 in each group. And then we can look also at the, I'm going to save looking at the means for within the groups because we can obtain that while we run the ANOVA. So what we're going to try to do is answer the question, is there a relationship between the group means for temperature and the dependent variable of problem solved? So the researcher hypothesizes that students will be able to solve different numbers of problems depending on the temperature of the room. The null hypothesis is that there are no differences among the means, and the alternative hypothesis is that some means are different from some other mean. So the first thing we're going to do is we're going to go up to analyze. There are multiple methods for getting an ANOVA in SPSS, but the one for the kind of ANOVA we're going to run, which is the one-way ANOVA when there's only one independent variable, is easiest to obtain under compare means and proportions, under analyze, and we'll see it down here, one-way ANOVA. So our dependent variable is the number of problems solved. And our factor, or independent variable, is group membership. We are going not to look at post hoc tests. Post hoc tests will be covered in another video or class, and so we're going to ignore post hoc tests for now. Post hoc tests are used after the ANOVA to determine where the individual group differences are among the mean contrasts. We are going to look at options, and what we want to get are the descriptive statistics. The fixed and random effects are not pertinent to this study. We're going to look, of course, at the assumption of homogeneity of variance. And then these two tests are used if you fail to meet the assumption of the homogeneity of variance test. And we'll choose one of them just so you can see it, but hopefully we will meet the assumption of homogeneity of variance, and we won't need to use the Welch test, which is less powerful. We may actually get the Welch, have to use the Welch test. I actually haven't looked at the homogeneity of variance test for this example. So we're going to then continue and note that by default, estimating effect size for the overall test is checked, so we will automatically get that. And we'll just go ahead and say, okay. So now we can see our group size and our mean for each group. The mean for the cold room is 1 problem solved, the medium room is 4, hot room is 1. So we already see that there looks like a difference. The question is whether the difference is statistically significant. Now we're going to look and see our homogeneity of variance test, because we always have to check that we've met the assumption. And this sig level is the probability. And the probability is actually here 1. If you actually double clicked on this, a probability is never exactly 1. Let's see if I can move this over so we'll see this with all of its, let's see, how do I do that? See the actual value. Well, I'm not coming up with it, but we won't worry about it here. But probability is never actually 1, so it's extremely close to 1, which is over our critical value of 0.05, which means that this homogeneity is very likely due to random error rather than any systematic difference in the variances, and that's good. Okay, we don't want there to be variances in between these groups that are different. So the significance test, we always want those to be above our critical value, our alpha of 0.05. So it is, so we can proceed to run the ANOVA. And here you see our ANOVA table. And the between groups sum of squares are reported, within groups sum of squares are reported, and total sum of squares are reported. The degrees of freedom for each group are reported. You'll note degrees of freedom for within or between groups is 2. That's number of groups minus 1, which is 3 minus 1, which is 2. And within groups is the total sample size, which is 15, minus the number of groups, which is 3. So that's 12. We see our mean squares. Mean squares are sums of squares divided by degrees of freedom. So in this case, for the between groups mean square, you have 30 divided by 2, which is 15. And you see your F ratio, which is mean squares between over mean squares within. And that's 11.25. That is significant. Okay, so statistical significance is obtained if the value in this column, sig 0.002, is less than your alpha level, and it is 0.05. So that means that you have rejected the null hypothesis of no differences among groups. And there are some differences among some means. And then you can go down to your ANOVA estimate. You're interested in the point estimate, and you're interested in this case of eta squared, because that's the one that we have studied here. You'll see the other ones which are corrected. We didn't do random effects, so we don't have to worry about that one. Omega squared fixed effect is also given in some of the material you studied, and you can see the estimate for that. It's considered an unbiased estimate, so it's always lower than eta squared. And so we can say, using eta squared, that approximately 65% of total variance is due to the differences between groups. And also we can remember that eta squared is the sums of squares between divided by the sums of squares total. So if you took by hand 30 over 46, you'd get that 0.65. And that is called, this F test is called the omnibus test of the one-way or one-factor analysis of variance. So now we're going to go on and take a look at the chi-square, get rid of this, chi-square goodness of fit test. And again, the data here are the same as worked through in step-by-step calculations on another video. The chi-square test of goodness of fit tests the assumption that your distribution of your categorical variable or your proportions of your categorical variable match some theoretically established distribution. So here we have test items, scored true-false test items taken from a publisher's item bank. And what we want to know is whether those meet the expected values of half true-false and half true and half false. So the first thing we'll do again is we'll look at the frequencies with which our actual observations occur and see frequencies are already over there, but we'll click to bring them over. And all we want here are the frequency tables. Mean, standard deviations aren't appropriate for categorical variables. And so we'll see that we have 90 cases and that 35 were scored false and 55 were scored true. So 39% were scored false approximately, and 61 approximately were scored true. And we want to run the goodness of fit test. Now, our null hypothesis is that there will be no difference in proportions between true and false, that the true and false are assigned to items. Items appear in a true or false format in a 50-50 way. They're equal proportions. And what we want to see is whether or not these proportions are different from that statistical assumption of a random allocation of true and false. So we go to analyze, and in this case, we go to what's called a non-parametric test list. A non-parametric test means that because these are both categorical variables, we don't apply the assumptions of tests where there are continuous variables. We are not assuming the normal distribution. And we're going to go all the way down to legacy dialogues and choose the first one, chi-square. So this is the chi-square goodness of fit test. It is not the same SPSS commands as our other kinds of chi-square, which we'll get to in a minute. So the variable that we're testing for the goodness of fit test is test items. And our expected values, okay, so we are testing our actual values against what they call expected values. The expected values are the values under the null hypothesis. In this case, that true, false items will be written in equal proportions in the bank and 50-50. So our expected values are that all categories, true and false, in this case we have two categories, will occur in equal proportions. And if we look at the options, you can get descriptive statistics. We've already kind of looked at that from the frequencies, and we can deal with missing data, but we have no missing data in this. And so we can just continue for here. And we press OK. So this is the chi-square goodness of fit test. It tells us that our actual assigned scores on these publisher test items are 35 false and 55 true. And our expected values are that they would be evenly distributed, 45 and 45. Now, in another example where it was worked out, I put in the expected percents of 50-50. Since this is a data set of 90 points, they just give the expected number, 45-45. It really doesn't matter which you choose. And all you see here is the chi-square test. And the chi-square value is 4.44. You note that A down there, which says 0% of cells have expected frequencies less than 5. And that is a if you have a very small number of cases in a cell, these cells are 35 and 55, then chi-square doesn't run properly and you shouldn't run it. If, God forbid, you have 0 cases in a cell, you simply can't run it. But we have no problem with that. And so we have our chi-square test, 4.44 is the chi-square statistic. Our degrees of freedom are 1. Our degrees of freedom are the number of categories minus 1. We have 2 categories. So our degrees of freedom are 1. And we have the significance level. And to reject the null hypothesis, we want the significance level to be under the value we've set of alpha equals 0.05. So it is, so we reject the null hypothesis, and we can say that the assignment of items or the proportion of items that are in the true versus the false condition under these publishers' test bank is significantly different than what would be expected. And actually, we can go ahead since we only have 2 categories, and we can say that true occurs more frequently than false. So that is our chi-square statistic and for the goodness of fit test. And now the last test we're going to look at in SPSS is the, let me close our chi-square test, and I don't know what changes I've made in here, but we're going to save those changes. So here we're going to run what's called the chi-square test of independence. And the chi-square test of independence tests the hypothesis that there are statistically significant differences between the proportion of cases that occur in 2 categorical variables. So we can look at this as a table where, well, I'll go ahead and show it as a table. It's easier to explain. But our setup here is that we have students assigned to a condition of treatment. And in this case, they've been assigned to either training in self-regulation, self-regulated learning, or no training. And we're calling training in self-regulation the treatment, and no treatment is control. So we'll look at the frequencies with which those occur. And assignment to condition is assigned 50-50. So we've used random assignment and assigned people in equal numbers to the control and the experimental condition. And what we've done is after the treatment, we've assigned them computer science programming problems, and we've observed whether or not they check their responses. And I'm going to quickly put in the value labels for that checking. If they have a 0, they did not check. And if they have a 1, they did check their solution. So now we have those value labels, and we can run the descriptive statistics on that and see that, let's see, bring it up here a little bit. 62 of them out of the 100 did not check their problems, and 38 did. So we have 100 people, so 62% did not check, and 38 25% did. So what we want to know is whether there's a relationship between checking and group membership. Do people in the control group check more frequently than people in the experimental group? Do people in the experimental group check more frequently than people in the control group? Is there a relationship? And the null hypothesis of this, which is called the chi-square test of independence, or of association, is that there is no association between membership in the two categorical variables. So to do this, we're going to look at what's called the crosstabs command under descriptive statistics. And it says this is a descriptive statistic, but we can actually get an inferential test here. But at first, all we're going to do, and I've already got these in, is we are going to choose the two categorical variables. And one of them is going to appear as rows, one of them is going to appear as columns. It actually doesn't make sense which you have as row and which you have as column. But in this case, this is just the way I've chosen to do it. I believe that it matches the example in another video. Now note, we can get statistics here. I'm actually going to uncheck this because I don't want to show the statistics at this point. We'll do those in just a second. What we are going to ask for, actually, it's just our observed counts. So we can check and see how many are in each what we call cells. And so I'm going to press OK. And we see that there were 50 people in the control condition, and 50 people in the experimental condition. Within the control condition, 36 out of 50 didn't check. Within the experimental condition, 26 out of 50 did not check. And these 36 plus 26 plus 14 plus 24 account for all 100 cases. Overall, 62 checked, or I'm sorry, 62 of the total sample did not check, and 38 of the total sample did check. And what we want to know is there an association between the cells? So is there a relationship between, for instance, being in the control group and checking? And so you test that using the chi-square statistic. The expected values. So where are you going to get the expected value? Well, if not checking, if 62 out of 100 people did not check, if there's no relationship between checking and control, you would expect half of the control group, half of the no checking people to belong in the control group and half of them to belong in the experimental group. So these things are your expected values. You expect 62 people overall not to have checked. And therefore, if there's no relationship, you expect half of those to have been in one condition and half of them to have been in the other condition. You can just look at that and see that that's not true. But what we want to know is if it's statistically significantly not likely for the distribution that we see to be different from the expected values. So to run that test, we go back to crosstabs. And in this case, we ask for the statistic chi-square. And it's really that simple. There are all kinds of information within the cells that you can ask for. You can ask for percentages. I'm going to include asking for the expected values, but you can ask for percentages. It can start to look kind of cluttered, but for descriptive reporting, sometimes you want to ask for those things. And so I'm going to say okay. So note that given 62% or 62 people answering that they didn't check, you would expect 31 in both the experimental and control. If there's no relationship, you would expect checking to be evenly allocated within groups. If 38% checked, you would expect half of those to belong to the control condition and half to belong to the experimental condition. So 50-50. So those are our expected values for these 31-31 and 19 are expected values to run the chi-square test. And here are our chi-square results. We're interested in the Pearson chi-square. We have no problem with the values of 0 or values in the expected of less than 5. So we have no rarely occurring values which can pose a problem for the chi-square. Our degrees of freedom are 1 degrees of freedom in a what we call a 2x2 chi-square are the number of conditions in the first factor, which would be 2, and the minus 1 times the number of conditions in the second factor, which is 2 minus 1, or j minus 1 times k minus 1. And so that's going to be 1 times 1. So we have a total of 1 degree of freedom. And the significance level of that is 0.39. Against, we look at our significance for the test of the null hypothesis that there's a relationship, or that the null hypothesis that there's no relationship between the groups, and our null, we're looking at an alpha of 0.05. What we find is a significance. Chi-squares are pretty much always two-sided, and we find a significance of 0.039, which is lower than our alpha of 0.05, so we reject the null hypothesis. And that is the SPSS walkthrough for the one-way ANOVA omnibus test, the chi-square goodness of fit, and the chi-square test of association. I hope this has been useful.